In the center of our galaxy, 26,000 light-years away, astronomers found something that breaks every rule we know about physics. It orbits a supermassive black hole at impossible speeds. It survives where nothing should. And we have no explanation for how it got there. For 20 years, scientists have been tracking this object. They call it G2. It's unlike anything we've ever seen orbiting a black hole before. Sagittarius A star. Our galaxy's supermassive black hole, 4 million times the mass of our sun, the most extreme environment imaginable. At this distance from Sagittarius A star, temperatures reach millions of degrees. Radiation floods space. Gravity tears matter apart, atom by atom. Nothing survives this close. Gas clouds evaporate. Stars are shredded. Yet G2 has been orbiting here for decades, completely intact. Dr. Andrea Ghez at UCLA has spent 3 decades studying the galactic center. In 2002, her team first noticed G2's strange orbit. Using the Keck Observatory in Hawaii, they tracked G2 through infrared wavelengths. Infrared light pierces through the dust clouds that block visible light. The galactic center is hidden behind 30,000 light-years of dust, but infrared sees through it, revealing the chaotic core of our galaxy. G2's orbital period is about 200 years. It swings close to the black hole, reaching speeds of nearly 5,000 miles per second at its closest point. That's almost 3% the speed of light. At these velocities, time dilation becomes measurable. Physics enters the relativistic realm. When astronomers first spotted G2, they assumed it was a gas cloud. That's what the spectrum suggested. Hydrogen and helium glowing from radiation exposure. Gas clouds near black holes don't last long. They're stretched by tidal forces, heated to millions of degrees, and torn apart within a single orbit. Scientists predicted G2 would be destroyed during its closest approach in 2014. Telescopes around the world watched. G2 made its closest approach. It dove within 200 billion miles of the black hole's event horizon and survived. No gas cloud could have survived. The tidal forces alone should have ripped it apart. Yet G2 emerged intact, continuing its orbit as if nothing happened. Something was protecting G2. Either it wasn't a gas cloud at all, or it had a structure dense enough to survive where nothing else could possibly exist. The leading theory emerged. G2 might be a star. Not visible directly, but hidden beneath a thick envelope of gas and dust stripped from its outer layers. A star would have enough mass and structural integrity to survive the extreme environment. The gas envelope would glow from radiation, matching what we observe. But this creates a new problem. If G2 is a star, how did it end up on such an extreme orbit around the most dangerous object in our galaxy? Stars in the galactic center typically orbit in a stable disk formation, carefully avoiding the most extreme regions. G2's orbit crosses right through the danger zone. Dr. Stefan Gillessen from the Max Planck Institute proposed a radical idea. G2 might be the product of a stellar collision. 2 stars merged into one. In the dense core of our galaxy, stars occasionally collide. The merger creates a single massive object surrounded by debris, exactly matching G2's appearance and behavior. Binary stars in tight orbits gradually lose energy through gravitational wave radiation. Over millions of years, they spiral closer together until they finally merge. The merger would release enormous energy, blasting away the star's outer layers. The core would survive, hidden inside an expanding cloud of stellar debris. Computer simulations of stellar mergers match G2's properties almost perfectly. The mass, the orbit, the gas envelope, every detail lines up with the merger scenario. But here's where it gets strange. Even if G2 is a merged star, it shouldn't exist in this location. The physics of how it got here breaks down. To reach its current orbit, G2 would have needed to be kicked by something massive. An encounter with another object that fundamentally changed its trajectory. The most likely culprit? An intermediate mass black hole. Thousands of times more massive than the Sun, lurking somewhere in the galactic center's chaotic core. Intermediate mass black holes are theoretical objects we've never directly observed. Too big to form from single star collapse, too small to be galactic centers. They're ghosts. If one exists near Sagittarius A star, it would gravitationally disrupt any object passing nearby. G2's strange orbit could be evidence of such an encounter. Scientists are now searching for other stars with similarly disturbed orbits. If multiple objects show the same pattern, it could reveal the hidden black hole's location. But there's another possibility that challenges everything. What if G2 isn't protected by a stellar core? What if the physics we're seeing is simply wrong? Some physicists propose that our models of tidal disruption near black holes might be incomplete. The equations work for most objects, but perhaps not for all configurations. The environment near Sagittarius A star is unlike anywhere else we can study. Extreme gravity, intense radiation, relativistic speeds. Our physics may fail here. General relativity predicts these extreme conditions, but we've never directly tested the theory in environments this violent. G2 might be our first real test. Over the next decade, G2 will continue its orbit, moving away from the black hole. Its behavior during this period could prove or disprove multiple theories. If G2 starts to fragment or show signs of tidal disruption now that it's past periapsis, it would suggest a loosely bound structure, possibly confirming the stellar core hypothesis. But if it remains intact, surviving the entire orbit without disruption, we'll have to completely reconsider what we think we know about tidal forces. The James Webb Space Telescope is now monitoring G2 with unprecedented precision. Infrared observations could finally reveal the structure hidden beneath the gas envelope. Every observation adds data to the puzzle. Temperature measurements, spectroscopic analysis, orbital tracking. Each detail constrains the possible explanations. Whatever G2 turns out to be, its existence has already challenged our models. It's exposed gaps in our understanding of the most extreme environments in the universe. And if an intermediate mass black hole does exist in the galactic center, G2's orbit might be the key to finally proving these mysterious objects are real. The search continues. Multiple observatories coordinate their efforts, watching G2's every move. Each observation brings us closer to understanding what shouldn't exist. Here's what we know for certain. G2 has survived 3 close passages near Sagittarius A star since 2002. It remains structurally intact. Its orbit is precisely measured, periapsis at 150 astronomical units from the event horizon. Orbital period, 197 years. The infrared spectrum shows hydrogen and helium emission consistent with gas heated to thousands of degrees. The luminosity matches a gas cloud several times Earth's mass, but deeper analysis reveals velocity patterns inconsistent with a simple gas cloud. Something dense anchors the structure, preventing tidal disruption. Current models suggest a stellar core roughly twice the mass of our Sun, shrouded in an envelope of stripped stellar material, the remnant of a violent stellar merger. The merger likely occurred between 100,000 and 1 million years ago. The gas envelope is still expanding, still glowing from the collision's energy. The encounter with an intermediate mass black hole would have occurred earlier, perhaps several million years ago, setting G2 on its current death-defying trajectory. This means somewhere in the galactic center, an invisible monster lurks. Thousands of times more massive than the Sun, never directly observed. Until now. If confirmed, this would be the first intermediate mass black hole ever found. A missing link in black hole evolution. Predicted by theory, proven by G2. But even if we're wrong about the stellar core, even if our models fail, G2 has already succeeded in pushing physics to its limits. That's the real discovery. G2 exists in a realm where our equations struggle, where predictions fail, where the universe shows us the boundaries of human understanding. Over the next century, G2 will complete another orbit. By 2214, it will make its next close approach to Sagittarius A star. Future generations of astronomers will continue the watch. They'll have telescopes we can barely imagine, instruments sensitive enough to resolve G2's internal structure. They might finally see the stellar core directly. Or they might discover something even stranger. Either way, G2 will continue teaching us about extreme physics. The hunt for intermediate mass black holes continues elsewhere in our galaxy. G2 might not be unique. It might be the first of many still waiting to be found. Understanding how stars behave near supermassive black holes isn't just academic curiosity. It's essential for predicting the fate of stars near the Milky Way's center. Every galaxy has a supermassive black hole at its center. Understanding the extreme physics near these monsters helps us understand galactic evolution across the universe. The data from G2 feeds into models of stellar dynamics, tidal disruption events, and black hole growth. One object, but implications spanning astrophysics. And perhaps most importantly, G2 reminds us that the universe still holds surprises. Even in our own galaxy's backyard, we're still finding the impossible. 26,000 light-years sounds distant, but it's practically next door in cosmic terms. G2 orbits the supermassive black hole at the heart of our home galaxy. We share this galaxy with G2. Both of us orbiting the same gravitational center, separated by distance, but connected by the same cosmic forces. The scientists studying G2 aren't just investigating a distant object. They're exploring the physics that governs our galaxy's evolution, including our own solar system's future. In roughly 4 billion years, the Milky Way will collide with Andromeda. Our supermassive black holes will merge. Understanding Sagittarius A star helps us predict that future. G2 is a preview of those dynamics, a test case for how stars behave during galactic mergers, a window into our galaxy's distant future, happening now. Every observation of G2 adds another piece to the puzzle, not just of what it is, but of how the universe works at its most extreme. That's why we keep watching. The universe doesn't reveal its secrets easily. But every telescope pointed at G2, every spectrum analyzed, every model refined, we get closer to understanding. G2 shouldn't exist. But it does, and in its impossible survival, it's teaching us that the universe is stranger and more wonderful than we ever imagined. What other impossible objects are out there waiting to be found? What else have we missed? Subscribe to Parallax and let's find out together.